Hi everybody, in the next few videos we'll explore yet another nice and interesting property of martingales, namely that under mild conditions they do converge. The first tool we're going to use for that is called upcrossings, so I'm going to tell you about upcrossings in this video. So I will start off with the process. Let's just draw a graph of a process. And so maybe it starts from 0, it doesn't need to start from 0, but maybe it starts from somewhere and it does some oscillations, and then maybe it does something like this. So this will be a process, and it's in discrete time. Everything we do in this unit is discrete time, but let me just draw it as a continuous curve. And so that's a process xn as a function of n, and then I'm going to draw two levels of values a and b. So we're going to fix a smaller b real numbers, okay, and so b is this value here and a is that value down there, okay. And I'm going to introduce some interesting quantity. So Cn is going to be the following. Well, first of all, I'm going to say that C naught is 0. It doesn't really matter. C naught is 0, and Cn is the following. It's defined recursively depending on what x does. So I start putting down an indicator that Cn minus 1 is 1, and an indicator for xn minus 1 smaller than or equal to b. And there is another part to this recursion. Indicator that Cn minus 1 is 0, and an indicator that xn minus 1 is less than a. Okay, that's what this is. Now this looks very strange and very unfamiliar, so let me explain a little bit. Think about this as an on-off process. So I'm going to refer to Cn equals to 1 as the process being on, and Cn equals to 0 as the process being off. And if you notice that it's the sum of indicators, well, first of all, these two indicators, Cn minus 1 is 1 and Cn minus 1 is 0, they can't be true at the same time. So these events don't happen at the same time. So at most exactly one of these two indicators will be 1, which means that this sum is really just this sum is not contributing at the same time. So this Cn process can never be 2. It can be 0 or it can be 1. Okay, so that already kind of justifies on-off because it's a 0-1 process. Okay, so why do I call it on and why do I call it off? So C naught is 0, and so when a previous value of C is 0, when the thing was off in the previous step, so this kind of marks the fact that the previous step the process was off, and here the previous step the process was on. So when does it turn on if it was off? When it was off, it turns on when xn minus 1 is less than a. So whenever it was off, it's turned back on when my process is below the level a, which means that immediately it's going to turn on, at least in this picture. If my process starts from 0, which is supposed to be below a at this picture at least, then immediately it turns on. It started with C naught equals off, it turns immediately on. Now what happens if it was on in the previous step? Well, it turns on, and then it's going to stay on as long as xn minus 1 is less than or equal to b. So it stays on as long as as the process achieves level b. Okay, so it stays on until this time here. If it was on before, it stays on until the process is below b. Now in the next step, when the process achieves b, when xn minus 1 equals or larger or equal to, well, actually if it's strictly bigger than b, let's say, so if xn minus 1 is strictly bigger than b and it was on before, then it turns itself off. So at this point, when we exceed b, it is going to turn itself off. Okay? So it turns to 0 because this indicator will then kill the whole thing. So the next Cn value is 0. And at that moment, we're going to have to look at the other side of this recursion. What happens if in the previous step my process was off, if it was 0? So if it was 0, then the first indicator doesn't play any role. I just have to look at the second part. And this indicator will turn it back on again as soon as xn minus 1 goes down back below a. As long as xn minus 1, as long as my process is above a, it stays off because this indicator is 1, this other part is 0, but this indicator for xn larger than a is still off. It still doesn't give you a contribution. So the thing stays off until xn minus 1 goes strictly below a. So until this point here, it is going to stay off. And then the process repeats. So it turns back on at this moment when the previous value was off and x goes down below a. It turns back on. So now I have to look at the first part of this sum because Cn minus 1 is on. And it is going to be on as long as xn minus 1 is below b. So it's going to do an on period again until this value. And this is how it goes on. So it's on until it comes back down below a. And it turns itself back on at this point, and it's on until it goes above b, and then it's off again, turns itself back on, and in this picture, at least until we see it, it's never turning off again because it's not going up above b. Okay, so that's what this on-off process does. Okay. Now a few remarks are in order. The first remark is that this thing is predictable. Cn is predictable. Of course, I'm assuming at this moment that the process X is adapted. So it's adapted to a filtration. And if you notice what's going on here, then everything that defines Cn is Fn minus 1 measurable, right? So this thing is Fn minus 1 measurable because it depends on previous values of C and it depends Fn minus 1 measurable values of X. So if X is adapted, then this thing is predictable. Okay, that's the first observation. And the second thing I want to do is I want to define Yn. Let's use a different color for this. I want to define Yn as the Martingale transform of the process X with this predictable C. So the notation we had for that was the C bullet X, and it was defined as the sum from 1 to n of xk minus xk minus 1 ck. Okay, this is how the Martingale transform works, and this is how I want to define the process Yn. Now, what does this do? So notice that ck is 0 or 1, 0 when it's off and 1 when it's on, and xk minus 1 is just the increment, the one-step increment of the xk. So I only need to look at this sum for the periods when ck is on. So I only looking at this sum on these periods where the thing is on. So I'm looking at this period here, and then this period there, and then this one here, and this one. Okay, these are the periods I'm considering x, the increments of x for this process y. And so what is happening in these periods is that ck is constant 1. So I'm adding up the increments of x from the left end of my period to the right end of my period. In other words, I'm adding up all the increment of my process x from this point to that point, and then from this point to that point, from this point to that point, and from here on to the end of this picture. Okay, this is what this Martingale transform does. All right, now let's keep this in mind. So essentially what this process does is just looking into all of my increments. Whenever I go from below A to above B, it's counting that. What is not counting is coming back down. So it's not counting from here to there, it's not counting from here to there. Anytime I come back down from above B to below A, that's not counted by Y. Okay? Now let's keep this in mind, and then let me define something else which will be very useful and which will be in the core of whatever I want to say now, and that's the following. I'm going to define the number un of a, b, and this is going to be the number of upcrossings. Number of upcrossings. Upcrossings until time n. Okay? For example, if this is my time n, I didn't draw my graph long enough, so let me just extend the axis. Maybe this is time n. Then the number of upcrossings will count how many times I went from below A to above B. Okay? And I'm going to formalize this in a second, but in this picture it's going to be 1 here, 1 there, 1 there, and the last one I don't count, so I think it's gonna be 3 on this picture. Okay, so let's formalize this thing. The formal definition is going to be the following. Okay, so I'm looking at the maximum integer k such that there exist times. I'm starting from 0, so this well, probably is not very important to say, but let's just fix that. I'm starting from time 0. So the number of times s1 smaller t1 smaller s2 smaller t2 and so on smaller sk, so I have k of these times, k many of these numbers, these times, all between 1 and time n, or 0 and time n, such that I have an upcrossing, such that x of the si's is always less than a, and x of the ti's is always larger than b for all i's from 1 through k. So it's really just capturing what I said. Whenever I can have a time interval such that the process starts from below A and it goes above B, I'm counting that, and I want to count everything, so that's why I take a maximum. The maximum number of intervals I can divide this thing such that I start from below A and I end up above B. Okay, so in this picture it's going to be 1, 2, 3 on periods. I'm not counting the last one because the condition assumes that x of ti is larger than b, and that doesn't hold for the last one. Okay, so this is the number of upcrossings. And then let's keep all of this in mind, and I'm going to come back to this picture soon and a lot of times, but let me now change sheet and tell you a very simple observation, namely, so an observation is the following. Which color should I use? I'm going to use the same purple. So the claim is, here is an observation, an easy observation from all of the above, is the following, that if I look at the value of y at time n, that's larger than b minus a times the number of upcrossings minus, I need a correction term, xn minus a negative part. Okay, and let's just see why that happens. So again, what is going on with this process? So yn is counting every upcrossing, every increment of my marting of xn, of the process xn, within upcrossings. So anytime I can see an upcrossing, I know that I started from below A and ended up above B. So any number of times I see an upcrossing, and that's counted by u, I know that my increment, my total change in this sum, was at least b minus a, because I came from below a and I ended up above b. So every time I see an upcrossing, this quantity counts that and adds a contribution of at least b minus a times b minus a. And then I have this number of upcrossings, so that's where this term comes from. Now at the end, I might have a little bit of a problem, because I turned the process C on here at this point, and I might not have gone above B again, so it stays on. However, it might end up below A, and that must be counted, that is counted in the process yn. That's why I do this correction here. If I end up at some level that's below A, then this might have been counted by the process yn, and that has to be subtracted, because it's a negative contribution, right? Because I started at level A and I might end up something lower, so that's a negative contribution. If I end up something higher, that's okay, but if I end up something lower, that will decrease my right hand side, and I need to take that into account, and that's exactly what this term captures. If xn is below A, so this thing is negative, then that quantity, that increment from A to the terminal value, is subtracted from the right hand side, and then it will make the argument true. So so then the observation will hold. And as a simple corollary, I'm going to now tell you a lemma, a very important lemma, which is called Doob's upcrossing lemma. And that's just a simple corollary of what we've seen before. Doob's upcrossing lemma is the following: if xn is a super martingale, recall that super martingales are those which are decreasing in, or at least non-increasing in, the conditional expectation. Okay, then based on this inequality, I have a bound, namely b minus a times the expectation of un ab, so the expected number of upcrossings, is less than or equal to the expectation of xn minus a negative part. Okay, that's Doob's upcrossing lemma. And to prove it, all I need to do is refer back to the statement here and stuff we have seen before. So to prove it, all I need to do is look at y, which was c bullet x. Remember, y was defined as c bullet x, so the Martingale transform of x with this Onoff process ck. And for that process, we have the above inequality, and so this is a super martingale as well, which is a property we saw when we first defined the Martingale transforms. The process C is an on-off process, so it's a 0-1 valued process, which is non-negative for non-negative C's, and of course it's bounded, so everything is fine. So with such processes, if X is a super martingale, then the Martingale transform is also a super martingale. If we have a super martingale, then we know that the expectation is non-increasing in n, okay, and y naught is just defined to be 0, just the empty sum. Martingale transform at 0 is always 0. So the expectation of yn is non-negative, it's non-positive. It's non-positive, right? The expectation is decreasing from 0, or at least non-increasing from 0. And that's it. So if you just plug in the expectation of this quantity into there, then you immediately arrive to the statement. So that's Doob's upcrossing lemma. In the next video, I'm going to show you how to use it for convergence of martingales.